A second concept, a second model, which we use to describe water cycling is Raleigh distillation. And did Turi talk about this one? Yes? Okay. I'll give you my own quick summary then. So Raleigh distillation can happen in any system. We've got, it's again just a mathematical expression to describe how the composition of a mixture changes, evolves, as you remove material from it, right? Where there is discrimination, fractionation, okay, fractionation for isotopes. So the stuff you're removing has a different composition than the stuff you start with. Okay. So is it Raleigh distillation? We can think about various different systems. One, you have to have a kind of semi-open system, right? You've got a pool of material that's evolving over time, but you're removing stuff from it. So you have to be removing the material that you produce through the fractionating process. So that gives it an open system condition. And you have to have fractionation in order for there to be a change in the composition of the mixture over time. All right, so those are the key conditions. And this is the equation. Again, if Turi introduced it, I'm not going to go through it much, but we can think, these could be our isotope ratios. They could also be ratios of anything else in the mixture, right? But our initial isotope ratio, our isotope ratio at some time in the future, the fraction of the initial mixture remaining, and then our fractionation factor, okay? Pretty simple equation. We can use it to calculate how a material evolves over time. All right. Here's my favorite example of Raleigh distillation. These guys are doing a technical Raleigh distillation experiment with a device known as a still. And they've got a mixture in one of these containers, right? Their mixture happens not to be, they don't care about isotopes, they care about a mixture of other materials. And you've got a liquid vapor exchange going on in there, and that's fractionating, right? One of the compounds in their mixture evaporates more readily than the other. That means that the product of that exchange reaction has a different composition than the starting material. And then they're removing that product over into this container over here, collecting it, right? But that means that over time, the material in their starting mixture evolves. The composition of their starting mixture evolves, right? And it gets more and more diluted, and this one gets more and more concentrated. Okay, that's the idea. We do the same thing in a cloud, except here we've got water in the atmosphere in a vapor phase. It's a mixture of isotopes. Let's say it's oxygen 18 and oxygen 16 mixed together up there. We have a liquid vapor phase change reaction, okay? And our heavy isotopes, our oxygen 18, always prefers to go into which phase? Where's it going to end up? What's that? Liquid phase. Okay, yep. So our heavy isotopes always want to go into the more tightly bonded phase. And so we're going to end up preferentially moving the O18 into the liquid fraction. What happens to that liquid fraction? It's removed, right? It falls out as precipitation. So we've got a removal of that material. And that means that our starting mixture is going to evolve in composition over time. Okay. So what's the implication for the water cycle? Well, what it means is that as we take air that has water vapor in it and we move it through the water cycle, right, every now and then it encounters conditions that cause precipitation, right, cause this phase change reaction to occur, cause the removal of liquid water from this pool of water vapor, right, gas phase water in the atmosphere. And each time that happens, we're removing something that has a different isotopic composition, and so we're forcing the isotopic composition of the residual water vapor toward lighter and lighter isotope compositions, right? We're removing more and more of the heavy isotopes, leaving behind more and more of the light isotopes. And we can take Lord Raleigh's equation and plop it up in isotope space here. So we've got delta values, and we've got residual fraction here. So we'd be starting over here, thinking about this from the perspective of the atmosphere, of the vapor. 100% of the vapor remaining. We've got some idealized particle, or parcel of air, right, that's got a bunch of water in it. And as we start to encounter conditions that drive condensation, the removal of water, right, then we're removing something that's got a different isotopic composition, right? That dashed line up there is showing the isotopic composition of the product produced at any point on this curve. And we're leaving behind, as we remove that liquid water, lighter and lighter isotope compositions in our vapor pool. Okay? What kind of fractionation do we expect here? I've got it right there. So who can read? Right, so we're going to expect equilibrium here, okay? And why is this? Well, for condensation to occur in the atmosphere, right, it's basically essential that the atmosphere be saturated, that we have 100% relative humidity. So, and throw into the mix here too that, you know, water droplets form very small, right, in clouds, and they hang out there for a while, right? They kind of, you know, they float around until they grow to a size where they can fall out of the cloud. And so the water droplets themselves are spending time in this saturated environment, and they're able to exchange isotopes, right, with the surrounding vapor. And so we end up with an equilibrium process, okay? So that E, that epsilon there, is our equilibrium fractionation factor. I'm not sure where they get the numbers for this one. It's kind of an odd equilibrium fractionation factor for water, but let's say it's an equilibrium fractionation of 5 per mil. So our initial product we produce, our first rain that falls out of this cloud, if we've got an isotope composition of 0 for the vapor, is going to be +5. Right? Over time, as we remove more and more of our water, our reactant, our water vapor pool in the clouds gets lighter and lighter. But that product is always pinned, right, to the composition of the vapor at any given time. And so even when we get out here to 10% of the water remaining, right, very, very dry air, we've got an equilibrium fractionation, and we're still producing rain that's offset by a fairly fixed amount. So, but one thing I want to think about here, if we think about this is very idealized, right? Might be experimental conditions or something, but if we think about the real world, there's a little element of complexity we have to throw in if you want to actually, you know, use the Raleigh model to think about a process like, or let's say, precipitation. So what causes precipitation in the real world? Yeah. Okay, so in the real world, the main thing that drives precipitation, it's hard to ask questions when you guys all have like slides in front of you on the I guess I got to stop putting the answers on the slides. What's that? It's blank? Oh, all right. I must have been smart and made it an animation. All right, so anyway, air mass cooling, exactly right, is what causes condensation, right? We can get this in various different ways. We can actually move an air parcel inland or further north where it's cooled radiatively. We can waft it into the atmosphere by pushing it over a mountain range, right? There's some decompression cooling that happens then. This is the saturation vapor pressure relationship there behind this. I'm not sure why it's all covered up, but it's a function basically of temperature, right? And so to saturate a parcel of air, we cool it. Right. What's the implication if we think about our Raleigh model? Right? Our Raleigh model really only has 2 terms in it. One is the initial composition of the mixture. The other is the fractionation factor. Which of those varies as a function of temperature? Fractionation factor. So Turi, I'm sure, pointed out equilibrium fractionation factors vary as a function of temperature. Yeah? Okay. So I'll do my little demo here, right? If you think about the vibrational energy of 2 molecules and their, you know, the propensity to break a bond is going to be related to that maybe. So which one's the heavy one? Which one's the light one? Heavy's over here, right? It's vibrating more slowly. It's got less of that energy, right? The energy's the same, but it's got less vibrational energy, right? Greater mass. And now let's say we heat them up a little bit, right? Now we heat them up a little bit more. We heat them up a little bit more, right? It becomes harder and harder to tell the difference between the two, right? So that's what we're getting. As you increase the total energy in the system, add heat, basically the discrimination between the two gets less and less. Okay. So temperature affects this. How does this change our Raleigh model? You guys already told me, right? As temperature decreases, as we cool that air mass and bring it through progressively more saturated, episodes of saturation, alpha gets bigger, and that's going to play into our Raleigh model here. And so if we actually drew a Raleigh curve that was more appropriate maybe for a real world distillation from the atmosphere, now we're plotting it in terms of temperature here. Okay, scaled according to the fraction of vapor that would be remaining, given those saturation vapor pressure relationships. Here we're seeing a 2 per mil for oxygen, for example, shift in the fractionation factor as we go from warmish conditions like we might have tomorrow to freezing conditions. And we can even throw into the mix, it's not shown here, but as we move across the freezing point here, there's a change in the fractionation factor. The fractionation factor between solid phase and vapor phase water is slightly different than the fractionation factor between liquid phase and vapor phase water. Okay? All of that just goes into saying that as the cloud is actually cooling, producing progressive rainout, we have a shift in these fractionation factors. And that actually produces then an increase in the difference, the offset, between the vapor and the precipitation that's produced from it. So another question for you here. Well, okay, so when we talk about precipitation water isotopes, a number of effects, right? Effects which were described early on as researchers were going around the globe measuring water isotopes in rainfall, and puddles, and lakes, and recognizing that, wow, there's all this variation in water isotopes in the global water cycle. Okay? And so one of those effects is the temperature effect. And the temperature effect is simply a description of the fact that if you go to colder places on Earth, you see lower isotope ratios in the water, the fresh water that's there. Okay? Does that make sense in terms of the Raleigh model we just talked about? Right? We basically have the explanation here already. Okay? Colder places on Earth, right? Water's coming from warm places, right? That's where evaporation happens. Most of the evaporation happens on Earth, right? Tropics, subtropics, places where we have lots of energy available. We happen to have lots of ocean surface area there too, right? And that's the source of water to the atmosphere, the dominant source. As we move further and further away, we move to colder and colder places, we move down these Raleigh curves, and it gives us lower and lower isotope values. Okay? That's basically the temperature effect right there. Okay? The fact that when we're in colder environments, we're further away from the starting point, we've lost more water to distillation. There's a tendency sometimes, even in the literature, to see people confuse this with the temperature dependence of equilibrium fractionation. And I just want to throw at you that that is not what causes the temperature effect. Right? In fact, if you look at this, it actually works the opposite way. Right? So the colder you are, the greater the fractionation factor, which means the heavier the precipitation you produce from the same starting vapor. Right? So that's the opposite of the observation we see with the temperature effect, which is colder temperatures, lower delta 18O and delta 2H. So just keep that in mind. I don't want to ever hear you say that the temperature effect described is a result of equilibrium fractionation sensitivity to temperature, okay? Okay. All right. Questions, discussion, thoughts? Is this stuff that you guys have all heard before? Yes. So the rainout is not one of the traditional, oh, sorry. She's asking, I'm supposed to repeat the question. So as you progressively lose water, is that a rainout effect, right? And that's, yes, that's what I would call it, as a rainout effect. Rainout effect is not one of the traditional effects that was originally described, but that's what's going on here, right? And I think that's a better way to think of it in terms of rather than thinking of it in terms of local temperature or precipitation amount or some of the other things that have been talked about, because really that's the process that's driving this, is how much rainout has happened since that parcel was last saturated with vapor.
Yeah, so the first rains, for example, in really seasonal systems,
yeah,
the first rains are going to be heavier than the last rain.
Exactly, yep. Well, yeah, so you need to think about it in terms of the history of the air parcel. So if you're standing at one place, right, if you're standing at a single place and watching what's happening over time, for example, with this front here that just came through that's producing this rain, we'll have a rain sample of it that we'll measure. We didn't do multiple samples, but I bet if you went out and measured it over time, collected 10 samples through this rain event, that it would get lighter over time. But the main effect that drives that is actually higher condensation levels through the storm. As the front proceeds through, that the condensation levels tend to lift and get higher. And so it's kind of analogous to the rainout effect, because that moisture that's forming higher in the atmosphere, that higher condensation level, that air has been lofted more, and so it's lost more water as rain out, to rain out since it kind of started. Does that make sense? Yeah. Okay.
Can you explain one more time the difference here with the temperature effect?
Yeah. Okay. It's I hesitate to dwell on it because it's kind of dumb, but it's right. Here's the thing. So if we go to this equation, temperature affects this. Okay. This is our Raleigh equation, right? And it really describes the temperature effect. Temperature affects this. Temperature also affects this, the F, right? It affects alpha through the thermodynamics, right? And the fact that as we cool the mixture, there's greater distinction between the two isotopes, right? It also affects the F in that the ability of the atmosphere to hold water decreases as you cool it. And so if you start with a certain amount of water and you cool, the more you cool, the less you can keep in the atmosphere. And so the lower F gets. All I'm saying is that what we traditionally describe as the temperature effect is driven entirely by temperature effect on F, on the fraction of water that's remaining, the amount of rainout that's occurred, and not by temperature effects on alpha. Okay? The temperature effect on alpha actually would push us the other direction, but that's it. Okay? All right. Now that we're all refreshed and well fed, let's move ahead.